So chapter 10 is on trigonometric interpolation and the fast Fourier transform. So if you think back to chapter 4 where we discussed least squares, when we used a model that was composed of the trig functions sine and cosine, if you remember, when we computed the ATA matrix as part of the normal equations, the matrix was diagonal. Okay, and that was the reason for that is because sines and cosines are really nice functions in that they are orthogonal. Now, when I say orthogonal, you should be thinking of the dot product or vectors that when their dot product is 0, vectors are orthogonal. Well, for functions to be orthogonal, there's a similarity in that when we take a dot product that's in the form of an integral of a product, we get an integral that evaluates to be 0. Okay, so the Fourier transform basically exploits the property of the trig functions sine and cosine being orthogonal. And so we're going to take a look at what's called the discrete Fourier transform, which is going to help us do this trigonometric interpolation, and this fast Fourier transform, which just by the name you can tell makes things fast or computationally efficient. So the first thing that I'll discuss is section 10.1, which is on the Fourier transform, and the first part of that is on complex arithmetic. So we're going to take a look at complex numbers, since it will be useful in the discussion of the discrete Fourier transform. So if we have a complex number, z, which is equal to a plus ib, where I, of course, is the square root of -1. A and b are real numbers. Z has a complex conjugate, which is z bar, where we basically negate the imaginary component. So let me make this a minus I times b. And we also have the magnitude of a complex number, which is denoted absolute value of z, which equals, or what's called the modulus of z, which is the square root of a squared plus b squared. Okay, and in addition to this, I'll also be talking about Euler's formula, which is helpful in proving some results about complex numbers. Okay, so Euler's formula goes by e to the I theta equals cosine theta plus I sine theta. All right, so one thing that's useful with complex numbers is to represent a complex number with its polar representation. So now I'm going to discuss the polar representation of a complex number. So this representation goes by the formula r e to the I theta. And so if we were to draw this in the complex plane, you can imagine that if we have the real axis, it's the horizontal axis, the imaginary axis is the vertical axis, we have a point a plus ib, which is here. That this point, if we basically draw a hypotenuse and label and draw a right triangle, if we label this the hypotenuse is r, and this angle here as theta. Okay, this leg is A, this is B. And so we have our representation where z is equal to r e to the I theta, which is equal to a plus bi, or ib, excuse me, a plus I times b, where r is equal to the modulus of z, or the magnitude of z, which is root a squared plus b squared, and theta is equal to arctan b over a. Alright, so why is this polar representation useful? It's useful when we go to multiply complex numbers. So, if we were to multiply z1 times z2, which let's say have polar representations r1 e to the I theta 1, and z2 has representation r2 e to the I theta 2, well, using properties of exponents, this equals r1 r2 e to the I theta 1 plus theta 2. And you can imagine that if we had points in the complex plane that were on the unit circle, which would mean r1 and r2 equal to 1, that basically when we have these points that are on the unit circle, when we multiply these 2 points that are on the unit circle, it's a matter of just adding up their angles that they make with the positive real axis, and just move the point accordingly on the unit circle, the angle theta 1 plus theta 2. Alright, so the next topic is on roots of unity. Okay, so for roots of unity, imagine we have an equation, z to the n equals 1. Okay, or if you wanted to think of this as z to the n minus 1 equals 0. The roots of unity are z equal to e to the minus 2 pi I over n. Or this is one root of unity, and the rest can be obtained by taking z and raising it to the k power, which equals e to the minus 2 pi I k over n for k equals 1 through n. Okay, so these are the n roots of unity, and if you notice, these roots of unity are all on the unit circle. Okay, and so if we consider z equals e to the minus 2 pi I over n, this is what's called a primitive root of unity. And so now I'll discuss what it means for a root to be primitive. So we state that the nth root of unity is said to be primitive if it is not the kth root of unity, if it is not the kth root of unity for any k less than n. Okay, so as an example of this, consider that z equal to minus 1 is primitive. It is a primitive square root of unity. It certainly satisfies the equation z squared equals 1. It also satisfies the equation z to the fourth equals 1, but it's non-primitive. It's a non-primitive fourth root of unity. And if you think about it, for any n, so I will note, for any n, z equal to e to the minus 2 pi I over n is an nth root of unity. Okay, and we're going to use this as a generator for the nth roots of unity.